Thank you very much. So thank you for giving me the opportunity to present here.
Just one thing. Probably if you wear that, either on your trousers, then maybe the recording will work.
But do I need to turn on something?
No, I think you just need to put it on. If you just click it on your trousers.
Okay.
There you
Good. So the motivation is that chemical reaction networks are ubiquitous, and you find them at every scale. And at every scale, these networks are involved in energy transduction of some sort. So you can go from the very small scale, where you can conceptualize a molecular motor as a chemical reaction network that takes chemicals from its surrounding, transform them, throws them back in the surrounding. Here we are dealing, of course, with very small sizes and very fast time scales, microseconds. You have them at the level at the cellular level with metabolic networks. You can go to a higher level, which are food webs, or even higher biogeochemistry, where you're now dealing with certain networks that are almost planetary scale and time scales that can be hundreds of millions of years. And understanding how energy transduction happen in those networks, this is kind of my goal. That's what So in Brussels, I was raised in the Prigogine school environment, where thermodynamics, non-equilibrium thermodynamics was always an important topic. And since there's been a lot of development in non-equilibrium statistical physics, I got back to my original interests for chemical reaction networks, I mean, what I was taught in Brussels. And that's how I got there. So I will give you a brief introduction. I will give you also a brief description of how we can develop a circuit theory to deal with complex chemical reaction networks, because describing them at the elementary level, meaning at the level of elementary reaction, is hard, and so it's important to have efficient coarse graining tools. But I will just give you the basic idea. I will not go too much in detail. And the main goal is to get to energy transduction. How can we understand chemical reaction networks as machines that take energy from the environment and transform it into other forms of energy, and application to metabolisms. Actually, the most concrete application will be metabolism. Okay, so let's set the stage. An open chemical reaction network, I will mostly care here about deterministic dynamics. We can do everything at the stochastic level, but I think it's easier to describe things at the deterministic level. So we are dealing with a description in terms of a vector of concentration. So this is a chemical reaction network. All the species here have a certain concentration. And they evolve in time according to chemistry, which can consume or produce them. The J is the flux of all the reactions in this network. And the stoichiometric matrix, this is really a topological object in the sense that it doesn't depend on the kinetics. It's only telling you with what stoichiometry a given species is involved in a given reaction. So that's if the species is internal, meaning, for instance, those species, that's it. But certain species are exchanged with the surrounding. So, for instance, this one. And it means that there's an influx from the outside. In that sense, my system is open. The fluxes in the simplest case, and to start with, we will imagine elementary reaction. So elementary reaction means that I'm imagining the chemical reaction as really molecules colliding with each other. I'm not hiding steps inside. That is a kind of effective reaction. It's really the two molecules coming and reacting. In that case, mass action law, for ideal solution, I will focus on ideal solution. Also there we can go beyond, but for pedagogical purposes, let's stick with ideal and homogeneous solution. have mass action law. So the flux of the reaction is a kinetic constant times the concentration to the power of the stoichiometric coefficient of the reaction in which the species is involved. So as I said, I will distinguish internal and external species, terminal species I call them sometimes, or chemostated species. Sometimes I'm using, I should stick to one word, but I know that I will switch between the words, so I warn you already. So sometimes it's terminal species, sometimes it's chemostated species, or exchange species. But the internal ones are always internals. Those are the ones that are not exchanged with the surrounding. And you see, I can split the stoichiometric matrix in two pieces, the part that acts on the internal species and the part that acts on the terminal species. Now, an important object are the cycles. So why are they called cycles? I will give you some examples later to show you this, but these cycles, they live in the space of reactions. And if you go through all the steps, it's a set of reactions that leaves X unchanged. Because you see, if I act on C and I get 0, basically X doesn't change. So it's also a basis, you can think of it as a basis for my stationary fluxes, because when this is 0, this is the steady state. And so, yeah, there are cycles because I go through this set of reactions and my X species have not changed as a result. The net effect is that my X species have not changed. I will distinguish the cycles of Sx that are also cycles of Sy. They are less interesting. Why? Because they don't change anything. If you go through those cycles, they don't change X and they also don't change Y. The more interesting ones I call emergent cycles. They are cycles of X but not of Sy. So those are sequence of reactions that make my internal species go back to what they were, but the net effect on the environment is non-zero. And now you can already kind of guess a bit the picture of a thermodynamic machine. If you remember from your courses, you're doing cycles. So what you have inside goes back to whatever it was, but the net effect on the environment is that something happens, so you can already kind of anticipate that these guys will play an important role in the story. Okay, now let's construct the energetics. The energetics in the simple case of ideal homogeneous solution is that we assign a chemical potential to every species in this solution, okay? So it means that in absence of reaction, we're dealing with an equilibrated set of species that have a certain chemical potential that is typically given by the standard chemical potential plus a term that is RT log of the concentration. Now, when reaction happen, they of course change the chemical potential, and the so-called delta G of a chemical reaction is the free energy change resulting from a reaction. It can be written like this. The stoichiometric matrix tells you how things change, multiplied by the chemical potential. So that's the change in free energy of every reaction multiplied by the flux through every reaction. That's the dissipation. Now for elementary reaction, it is easy, it's a very well-known result, that the log of the ratio of the forward and backward flux is related to the delta G. So if you plug this here, this structure J times log J plus J minus ensures that this quantity is always positive. And that's kind of the version of the second law. If you have elementary reaction with mass action law, this quantity will always be positive. And it's only going to be 0 when G plus equals G minus, which is when all the fluxes balance each other, so all the net fluxes are 0. That's the definition of equilibrium. Okay, it's a little bit of algebra with the ingredients that I gave you. You can show that you can rewrite the entropy production, that quantity, as work minus the change of G, where G is, you see, the average of all chemical potential times the concentrations, and a term that is RT that contains all concentration, so that term is the total concentration in the network. So it's a kind of average chemical potential. That's the free energy of my entire chemical reaction network. And the work is alpha only chemostat. So these are really it's a chemical potential that I bring in by having fluxes going in or out of my system. So it's really the energy that I'm bringing or removing from my system. With that, you already see that if I don't do any work, if my system is closed, this has to be positive. So I have minus delta G, that has to be positive. Any initial condition will go down in G until I reach equilibrium. So it's my Lyapunov function. So this is the statement that in a closed system, free energy will always go down until you reach equilibrium. And you can also show that the G is always greater than the Gx. It's a property of relative entropies. So that's to be expected. However, if you bring work in from the outside, you can lift the free energy. Okay? So this is the essence of thermodynamics of chemical reaction network at the elementary level. Good. So these are really the core ingredients. If you have questions, feel free to ask.
I always get, I know it's correct, but I always get slightly spooked by the minus RT term in the G.
Yes.
Is it?
So that guy is only, what I can say, is only going to play a role if your reactions are multimolecular. If you have reactions like A gives B plus C. Because if you have reactions like A gives B, or A plus B gives C plus D, you preserve, this term is always constant. And it plays a role, I mean, you can justify it microscopically. It has to do with the entropy of solute molecules in the solvent, and you can get it out from there. But
the Z is a
concentration.
So is it the next term in the expansion of the logs? Is that what it is? Because you get the x. You basically got x log x, right?
It's This is x log x.
Not
exactly.
Not expansion of the factorial. You know, the Stirling approximation.
It comes from there, but when you take into account the solvent is important to get that term. But yes, it comes from there. Because it's an ideal system, so everything is entropic.
Yeah.
But the fact that it's not pure Shannon entropy, as you would have in a stochastic process, because in a stochastic process probability is conserved, here total concentration is not conserved.
Yeah.
So you have a correction that is that term.
Yeah.
Good? Okay, circuit theory. We know, I mean, this is, I like to give this to engineers. In electronics, people don't solve Maxwell's equation in these geometries. It's a complete overkill. And so we have these Kirchhoff laws that we use to analyze efficiently circuits. And there's an whole industry around engineering this. And the question is, can we do something similar for chemistry? And that's exactly the message here. Yes, we can do something similar for chemistry. So the idea will be to have modules and to define the IV, the analog of IV. By IV, I mean current voltage characteristic of chemical modules. And then we will be able to analyze the network as modules characterized by an IV that we connect with each other. Why? Because it's an overkill to describe a chemical reaction network in terms of elementary reactions. If you just think of an enzymatic reaction, it's already not an elementary reaction. An enzymatic reaction has many steps. People spend decades characterizing all the steps of a given enzymatic reaction, so we need tools to go beyond that. That was my big fear at the beginning, and luckily it can be overcome. So I will give you, by example, the theory, not going into the details, but the idea is the following.
So on the other pocket, because it's rubbing against the plate.
No. So define modules with the rule that they should not share the same species. So if it's enzymatic reaction, don't create two modules that share the same enzyme. all the internal species in a module need to be specific to that module. But that's it. Then, calculate those emergent cycles that I mentioned before of the module, because each module defines an open chemical reaction network where the species that enter are the terminal species and the ones inside are the internal species. Now, every emergent cycle will define an effective reaction, and the value of the chemical potentials of the external species will be like the voltage. So the IV is the current along those effective reactions as a function of the voltage, which is the chemical potential of those external species. This is just, I will show you a more concrete example later, but this is to show you how it looks like. If you do this reduction for this big network, you can do it once, and you get that. But you can repeat the process and now treat the entire box as a module and further reduce it to that. So basically you went from a network like that to a network that has 3 reactions. And so if you can, you could do it analytically. If what is inside you can solve, get a steady state, then you can, it's a powerful theoretical tool, but you can do it numerically, or ideally you would do it experimentally. You would try to measure those fluxes as a function of the concentration in the range that you're interested in, and then you would get the IV of the module. Just a quick example, the simplest one of how it works. Let's look at this chemical reaction networks, which is detailed here. I write the stoichiometric matrix of that network. I split it into the part that is acting on the internal species, the part acting on the external species. That network, believe me, linear algebra has only one cycle, and that cycle is an emergent cycle. Let's see how it looks like. It's this guy. So it tells me reaction 1 once, reaction 2 once, reaction 3 no. So what do we do here? We do this. We do suck, suck. What is the net effect? Inside, we are back to where we were, but we took S in and we split NA out. So the effect is that we have an effective reaction corresponding to that emergent cycle, which has a stoichiometry that is given by acting with the SY part on the emergent cycle that defines the effective reaction. The stoichiometry of the effective reaction, and the flux will define the IV. That's another example. I go quickly here. In this case, there are 2 emergent cycles, and therefore that module will be characterized by 2 curves. And why did I pick that example? Because that's an example with internal cycles. But I want to go quick on that, otherwise I will not reach here. By the way, how much time do I have?
Until just before 4, so you've got loads of time.
Okay. Okay, there's the analog of Kirchhoff law, because if you go with the delta G along internal cycles, you get 0. There's the analog of a Kirchhoff current law, because basically you can write the dynamics for the terminal species in terms of the IVs of the modules. And so it really looks like a circuit theory in electronics. And the most important point, that was my number 1 worry at the beginning, was that when we coarse grain, we generically screw up the thermodynamics. But this coarse graining is thermodynamically consistent in the following sense. At steady state, my statement is exact. If I have a time scale separation between the internal dynamics of the module and the dynamics of the terminal species, my statement is a good approximation. The entropy production of my whole network, was, as I showed you, the sum over every elementary reaction flux times delta G, is now a sum over the effective reactions of my modules times the current along those modules. So I don't lose dissipation by doing this construction. I keep track of all the dissipation in my network. And notice that here I needed the information about all the concentration inside my network, while here I need less and less things because I only need the chemical potential of the external species, the terminal species. So there's also a gain from the point of view of having to know the chemical potential of only the external species.
But this is also still for all the elementary reactions. All the reactions are elementary.
So the statement is, at the elementary level I showed you before, that the dissipation is this. I need to know the flux and the change in G, so the delta G of every single elementary reaction. Now I'm showing you what I'm claiming. I'm not showing you. But I'm claiming, I'm proving, I can prove that at steady state or with time scale separation, all this dissipation here is captured just by the current along those effective reactions of the modules. So graphically, let's go back to this. It means that I had to know all the fluxes here, but actually, I only need to know these fluxes here, and these chemical potentials here, and I know the dissipation of
My
them.
question is, this Kirchhoff law analysis is only applicable when you have elementary reaction. Like if you have Michaelis Menten or anything like that.
Yeah, no, that's a very good one. So you can treat, this theory also tells you that you can treat as elementary reaction any scheme where you are confident that there is a single emergent cycle inside. So in other words, a module that is described by a single emergent cycle can be treated as an elementary reaction. And that's the very good news, is that most cytosolic enzymes, Michaelis Menten, they are a single emergent cycle. So you can treat them as elementary, and you just need the Michaelis Menten IV, which is well known, and that you can use it there.
And roughly speaking, that means they always take in one fuel and spit out one waste or something. They always do the same.
Yeah, it's like there's only one path that you can take to go from input to output.
Yeah.
The problem is if you have multiple paths, you need to be able to resolve which path it went through in order to characterize the full dissipation of the system. Yeah, that's the idea. Good. Now, okay, that's just to show you how you can take respiration with glycolysis, Krebs cycle, respiratory chain. For those who are, I think in bioengineering, you are familiar with that, no?
This is fine.
Okay. But this is basically how you extract energy from sugar by producing ATP. And you can split this into those different modules. It was interesting to see that what biochemists do is actually quite close to the notion of module. The only thing was for respiratory chain where we needed two modules rather than only one. And you see that what was also remarkable to me was that this central metabolism, this is from yeast, has only one emergent cycle. This was a priori not obvious, right? You could imagine that there are multiple pathways. And the stoichiometry of the emergent cycle is written here. Here you go once, here twice, you see? But some reactions here, 10 times, 12 times, 22 times. The net effect of all this is this. It's quite remarkable. And this you can split into these different modules here. So it's a powerful tool to analyze more complex networks. And to deal with enzymatic reaction in a way that is not too crazy. Okay, so now let's go to energy transduction. What is energy transduction? This is like a drawing to give just the idea. The idea is that in order to lift a small mass, that is something that should not happen. So I would hide this, right? You cannot see a mass going up. Well, it can happen if, of course, you attach heavy mass and the two processes are coupled so that the heavy mass allows you to lift the small mass. That's the essence of the idea. So let's start with a very simple, so-called tightly coupled chemical reaction network. That's kind of as simple as it can get. A and B become AB and split A plus B minus, and they split in A minus B plus. Okay? So the two processes are tightly coupled in the sense that there's only one way, one path to go from here to here. I will always take the convention that the spontaneous direction, the delta G, is negative when going from plus to minus. Okay, so Here, this is the spontaneous one, A plus wants to go to A minus, but B plus wants to go to B minus. So if there was not a coupling here, that process would never happen in this direction. It's just because that thing is pushing this one that this one goes this way. Okay? And it's tightly coupled because there's only one pathway. So the two processes are this one. I'm thinking of it that this is the atoms here are the same as the atoms here. The atoms here are the same as the atom here. You can think of it as a reorganization. But a process will be defined as something that preserves the atomic numbers. And if I write the dissipation for this, it's the flux times the change in G between this guy and this guy, and the change in G between this guy and this guy. But the flux is the same, so the flux actually, when I care about how much of this guy, which should not happen spontaneously, can be produced based on this one, this is my definition of efficiency, the flux drops. But that's specific to this tight coupling. In general, it will not be the case. And so this efficiency, because of the positivity of the second law, is always smaller than 1. Okay, let's go to the next level of complexity, where we have a loosely coupled system. Because you see here, my network is again going from A plus to A minus and producing B minus into B plus. That's the non-spontaneous process. That's the spontaneous process. But I have two pathways now. So they are not tightly coupled anymore. And if I analyze this, I will have one flux that is associated to this reaction and another flux that is associated to this one. I have two emergent cycles in the language that I was defining before. And now when I take the ratio between the output and the input with a minus sign because that's negative. It's also bounded by 1, but now that ratio depends on the current. So that's more complicated because if I want to assess the efficiency of that network, I need to know the kinetics. And that's something that is much harder than knowing just the free energy of the species, the terminal species. And so the question here was, okay, can we go beyond that? Can we say something smarter than just saying, okay, this is below 1, but then the ratio will really depend on the kinetics. So, and we want to proceed without having to go into kinetics. Only using the network topology and the knowledge of the chemical potential of the terminal species. And the answer is yes. And that's where this concept of gears come into play. So there's a way, gears are actually external cycles. They are not, emergent cycles constitute a basis. These elementary flux modes that act on the external species, it's kind of overcomplete. Some of them can be linearly dependent from the others. But essentially they are cycles. If you complete them once, you see that the net effect of the internal species is nothing, but the net effect on the external species is something. And they are elementary in the sense that if you remove any reaction, you break their cyclic property. That's in that sense that they are elementary. And there are well-established algorithms in system biology to find them. Actually, these algorithms get a bit slow when you deal with large networks, so this is still an issue. But they are typically interested in all of the elementary flux. We will only call gears those elementary flux that involves the external species. And the statement is the following. I will now associate to each of these elementary flux modes that I call gears, the efficiency, because each of them has a certain efficiency. Here, you see this one, for one A plus converted in A minus, produces 2 B pluses from B minus. While this one only produces 1. From 1 A plus to A minus, I produce only 1 B plus. And this one actually doesn't produce any output. So that one actually will have an efficiency 0. You could also have the opposite, one that only produces this actually by linear combination, and doesn't produce this, it will be infinity, but you will see those actually don't count. They will not play a role in the theory. The important ones are those that involve both input and output. And we have the following result. While the second law would only tell us that efficiency of the network is smaller than 1, independently of the operating conditions. What I mean by operating condition is the concentration of the terminal species. We can prove that the efficiency of the network is bounded by the optimal efficiency of the gear leading to that optimal efficiency. So you search across the different gears under a given operating condition, and the one with the maximum efficiency gives you the upper bound that your network can reach. Okay? So that's what is written here. The maximum over all efficiency of gears sets the maximal efficiency. So let's look at how it works here. So this is for the network I had before, that is drawn there. And we have 3 gears, but one we said efficiency 0, so that one doesn't enter here, because these are all efficiency below 1 and non-zero. And we plot as a function of you can think of it as the concentration of the output, so which was B plus, right? B plus is what we're working against. We want to produce B plus. The more B plus there is, the harder it is to produce B plus. So you can think of it as, I drew the little bag there to get an analogy. You can think of it as the slope against which you have to work is getting higher as you move along that direction. And this is setting my operating conditions. Now, under a given value of these operating conditions, here, in this region below 1/2, I have 2 available gears. This one, the alpha one, and the beta one. So these 2 ones are available. So, meaning their efficiency is between 0 and 1. In that sense, they are available. Let's get an intuition for it. Why is this one the best one, the alpha one? Because the alpha one is the one that for 1 A plus burn gives me twice a B plus. So obviously it's better than this one. However, as you start increasing the concentration of B plus, the slopes gets harder and harder. You don't have the resources anymore to fight against that slope. And so that gears, boom, stops being available. When it goes above 1, it's not possible. And now the only one left is the beta one. And so the optimal one that you could reach is this one. So that's a bound, only given by topology and concentration of the terminal species, what I call operating conditions. Of course, how to get there, this is kinetics, right? And what is quite remarkable, I will show you a toy model that will do the kind of ideal scenario, because if you have a well-tuned bike, what you want is that when the slope becomes too high, you change gear, look, and you go to the next best gear. And so what we want is to stay here, switch gear, and then be on this gear. Well, toy model, just playing with, it's a caricature of an enzyme with substrate inhibition. Because you see that if I have a lot of S here, I'm going to get into this E star that removes the enzymes from this reaction. So a lot of S shuts off this reaction. And does the opposite here, because a lot of S frees a lot of E2, and so activates this reaction here. And of course the opposite is true. When S is very low, I'm going to shut off this one and turn on this one. These are the gears of these networks. It looks very much like what I drew before. In the dashed line are this topological ideal case. But you see now that the enzyme, I can tune my kinetic rates. Here, I mean, I don't go into the detail of the kinetic modeling, but it's just playing with the kinetic constants of these things for different value of the kinetic rates. And I can tune the kinetics such that I'm very close to the optimal gear below 1/2. And I change gear, I mean, sometimes a little bit it's bad here, but it gets better after. Here it's better here, but it gets a bit worse after. But you see, it's still pretty good. I change gear in the intermediate region, and I get to my next optimal gear afterwards.
What's Q?
So Q is a combination of it's a way to parameterize the enzymatic kinetic constants of my enzymes. I didn't go into the detail of but this, I assume mass action kinetics here. So it's a few rates, and think of this as changing the kinetic property of these reactions. Okay. So that's actually a very good news. I was surprised how easy it was to, and kind of the picture that we are now asking is metabolism basically regulated like that, where you kind of have optimal metabolic pathways and enzymes that are switching between different metabolic pathways depending on the conditions you're working on.
Just a question.
Yeah.
What assumptions were behind getting that bound?
So actually, very little. So if we go back to assumption is that the starting point, the starting point, the metabolic network I start with, is composed either of elementary reaction or of effective reactions that contain only one emergent cycle. Provided this, the rest is topology, and even I assume I presented here ideal solution, but if you replace concentrations by chemical potentials, it even works for interacting mean field solution in the mean field regime. So it's actually remarkably few assumptions. Yeah. But the starting point needs to be thermodynamically consistent. That, I would say, is the stronger requirement. You need to make sure that there's no hidden dissipation behind those reactions. Okay. Yeah, let me skip this. Now the question is, this is the same concept but for a molecular motor where we analyze the gears. Okay, now actually that's a good answer to your question. I should have mentioned this. I assumed one input, one output. That's an assumption. But now I will show you that we can actually generalize this. So what if we are not in this scenario where we have one input, one output, but we're dealing with a network that has many chemostats, many terminal species, and a priori, what is the input, what is the output is not trivial. How do we define efficiency? How do we define a chemical process? It's a bit more involved, so this proper explanation would require half an hour on its own. So I will try to give you a sense. The important thing is that this can really be implemented as an algorithm at the end. So let me give you a flavor. The first thing is we need a bit more information than the stoichiometric matrix to define processes. We need the atomic composition of the species. Actually, we don't need all of them. We only need the atomic composition of each of the terminal species. Why? Because I want to make sure that when I call something a process, like G going to C, this is not, I don't have creation or destruction of matter in my process. A process needs to have same atoms here, same atoms here. Okay? So the atoms get shuffled in my network, but at the end, the net effect is that I have the same atoms here than atoms here. That's the first thing. They are elementary in the sense that I need to make sure that they are composed of the same atom and they are linearly independent. So here I gave you an example. For instance, these three here are linearly independent. So B to C, B to C, G to B, and ATP to ADP. Because I could create G to C by linear combination of these three. Okay, so an example of composite process is here. So G plus 2 ADP gives C plus 2 ATP. So that would be the composition of this and this. Okay, so, and then of course you can choose a basis. You need a basis. There's a certain freedom in how you choose your set of processes. But you need to find this set of elementary processes that are linearly independent. And you will express the transformation that the network does in terms of those processes.
Is there a typo there in the bottom one? Is it ATP on the left-hand side in the composite process?
G plus ADP, this is this, goes to C. No, I think you produce twice ATP.
Because it's doing a combination of the first reaction and the
No, then you need to take this plus minus twice this. Yeah, so I went too quick. It's this minus twice this. That gives this. But you see, it's a way. It's kind of a basic representation of what the net effect of your network can be. You can express every change on the environment in terms of a set of these elementary processes by linear combination. The second thing is you need a reference equilibrium. That's often very confusing, but I will use an analogy that will give you a good sense of it, I think. If you study a heat engine with 3 temperatures, you need to choose a reference temperature to define a temperature gradient, right? So you need to say, okay, what's going to drive my process is the temperature difference between this and this. Where now I chose this as my reference. And it's the same here. So the easiest way to think of it is, if I would only have one thermostat, and this one would not be there, my system would be at equilibrium. The ones I add, they create gradients, and they drive my system away from equilibrium. Because chemical reaction networks are a bit more complicated, you can have 2 or more chemostats, and your system is still at equilibrium. This, again, is a story on its own. It's because of conservation laws. If when you add the second, you would think the first chemostat is always going to break total conservation, but you need 2 in order to have a flux, you need to break, of course, one, the conservation laws. But the second chemostat that you add may or may not create that flux, because if you break, I mean, I know you're not following me, but it's just to tell you that it can be done algorithmically. If you break a conservation law, it's not going to create a flux. If you don't, it's going to create a flux. In this case, if you take these 2 chemostats and no other, okay, so these ones are not chemostated, you let them free, your system would still be at equilibrium. Maybe to give an intuition, if I put these 2 as chemostat, this reaction will go on until I accumulate sufficiently of this guy, and then the reaction will stop. So these 2 guys are not enough to drive my system away from equilibrium. I will not have a flux going through my system. I need more. And these are the guys that if I add those now I go out of equilibrium. Okay? So that's what I need. I need a reference equilibrium. So once I have this, and again there's a certain arbitrariness. The natural choice, this is what engineers do when they define X of G, they take the lowest temperature reservoir, which is the atmospheric temperature, because that's the most abundant temperature that you have around you, and you're going to dump all your heat in the atmosphere. Eventually it comes back, but they didn't know this last century. But this is the idealization of a chemostat, right? And so in chemistry, it's kind of the same idea. You will choose as your reference equilibria the most abundant thing in your environment, and the other ones are as the resources with respect to those environments. Okay, there's a certain arbitrariness in the choice, but the procedure is uniquely defined in the sense that the number of elementary processes is always the same, and the number of reference equilibrium species is always the same.
So in this case, you've chosen ADP as your reference,
Yeah.
which
C-
almost certainly is less abundant than ATP.
Exactly.
But that doesn't really matter.
That doesn't really matter. As in engineering, you could choose the hottest temperature as your reference, but it simply kind of makes things a bit less intuitive to understand. It's more natural to take your reference as the most abundant stuff. And so indeed, now I'm going to take my ATP as the resource, the thing that drives my system out of equilibrium, and my glucose as the resource. Good. I have my elementary processes, I have my reference reservoir, my reference chemostats or terminal species. I can show that the entropy production now is going to be expressed in terms of these elementary processes times the delta G of these elementary processes. You see, now I chose these processes in such a way that they always go to the equilibrium, so to the lowest point. And by writing my entropy production in terms of these flux forces every time, I will pick those that are positive as my resource, because they go down, they are favorable, and those that go up as my output. And the efficiency is, again, the same logic. Take as denominator the input, numerator output. So the logic is very similar as before, but we had to do this elementary step and reference equilibrium in order to go beyond one input, one output. You now look at the gears. Each gear will carry pieces of those processes. So for each gear, I can assign an efficiency. And the result is the same as before. The optimal transduction under a given operating condition is going to be given by the gear that gives you the highest efficiency. Okay, that's a summary of the thing. We implemented it as an algorithm also. And now let me show you how it works as an application. So we go to, this is the chemical reaction network describing glycolysis and gluconeogenesis. So glycolysis is using glucose to produce ATP, the net effect of all these. So glucose goes into pyruvate, and the net effect is that you produce ATP. So I think I wrote it here, yes. This is glycolysis. And this NADH is what later goes to produce further ATP if you add Krebs cycle and electron chain. The opposite, the gluconeogenesis, is, and that happens when your sugar level, for instance, in your blood goes down. You can actually convert back pyruvate into glucose. It costs you now some ATP, but it allows you to lift your glucose levels up. And this is kind of a textbook example of highly regulated thing, because it's clear that you don't want to do the two things together, right? Because then it's a kind of complete futile cycle. On one hand, you're burning glucose to produce ATP. On the other hand, you're going backward. Because, yeah, I should point out that these are you see that different reactions here, because different enzymes are involved in catalyzing the gluconeogenesis versus glycolysis. So it's like having two highways going in opposite direction. Doesn't make much sense. So that thing should be highly regulated. But again, regulation is kinetics, very hard information to get. Here we will do the efficiency analysis. So we pick this as our elementary processes. We can decompose the entropy production in terms of that. And the available gears that we have are all these different gears here. Okay? I can tell you that, my wife is a biochemist. When I showed her that, it was a test. The first reaction was, this is nonsense. Some of these gears is nonsense. It will never happen. Because they have this intuitive knowledge of what enzymes allow and do not allow. I don't do that, right? This is purely, from a purely thermodynamic perspective in the space of all possible kinetics. Actually, it's the next challenge to start using kinetic information to get rid of some of these gears. But you can now look at here the operating conditions. So you see here, you can think of this as changing here the pyruvate concentration here and here. And so we are in 2 dimensions now because we are more processes, but we focus on this region, which corresponds to the physiological region for E. coli. And we move along this line here. Okay, for the sake of simplicity, because in 2D it's harder to see gears, although they are represented here. But we take this slide, so think of it as here, we increase, we increase pyruvate or lower glucose is the same. So as I move here, this is high glucose, this is low glucose. And I plot all the gears that are available in this physiological region. Now the dotted line that go like this I should have mentioned before, 1 over the efficiency is when you ask the opposite thing, right? If now a given input can produce an output, but under different operating condition, the input can become the output and vice versa, right? So this is actually gluconeogenesis in the convention that we have. This is the inverse of the convention that we have, so minus it, but which corresponds to physiological direction of gluconeogenesis, meaning pyruvate to glucose. And you see that the 2 physiological reported things, like glycolysis and gluconeogenesis, they are actually available in the region of physiological conditions. So this is good news. It's a sanity check that the 2 processes are allowed. So there's potential for regulation. What is a bit more surprising, and okay, try to rationalize it, but you should not take us seriously because we are really not biochemists, is that there are other gears that in principle could be possible here and that do not seem to happen. So maybe we could exclude them with kinetic arguments, or you could say, but this is like theoretical physicists doing biochemistry, or maybe what you want is to make sure that over the entire range, only 1 mode is available, because those ones, you switch from one to the inverse, maybe that's not good, because that's harder to regulate, but you should not believe me. This is pure speculation, okay? The point is, it seems to work, and the challenge would be to exclude further gears using kinetic arguments.
Are they the most extreme? Because on that graph, they're the most extreme.
No, you see, in principle, that would have a higher efficiency than this one. So you could do...
That's what I kind of mean. One of them is the most loaded one way, and one of them is the most loaded.
Yeah, that's this one. But even if you compare producing ATP from glucose, this would be the available gear, right? So it would be best to be in this region. But in practice, we are here.
Yeah. So it's not the best, but like the 2 lines you plotted are the most extreme ratios. And there were other cycles you had. There were other. But so of all the ones you saw, are the real ones the most extreme ones?
But by extreme you mean
well, like because the blue line is furthest to the right, and the purple line is furthest to the left.
No, so those I excluded with respect to the previous line. I skipped a bit that argument. You can exclude some if you care about a flux that has a given direction. You can exclude those that are incompatible with the direction of that flux. So that's why you have less gear here than what you had on the previous plot. So I already eliminated some. But those that are compatible with the observed flux direction are those ones. And still out of those ones you have the non-observed ones that are in the middle here. And
it's your neutrino.
What?
It's your neutrino. You predicted it.
But I would want to... The first easy thing would be to use kinetic properties that we know about maximum velocities to rule out some of these fluxes.
My question is why in nature it should select the thermodynamically most efficient one?
Very good
With
question.
other-
Yeah, thank you. Of course, that's a hypothesis, it's a working hypothesis, and I agree that for sure it's not always the case. So I'm sure there are many other factors, but this is kind of, we want to test that actually on the next one, which is respiration fermentation in yeast. For the first time of my life, I'm starting to do experiments. Because what we want to do now in yeast, where they have a known transition between respiration and fermentation, we want to see if that transition happened precisely close to the point where what we predict is a switch in efficiency between respiration and fermentation. And of course, the true answer is I don't know. But I think for the first time we have tools to properly assess the thermodynamics. And so I think it's a very meaningful hypothesis to say, let's check if the transition is somehow related to a thermodynamic efficiency or not. And okay, my time is over, but the last comment I want to make, this is also very different from what you hear in textbooks or biochemists. They often like to speak of efficiency in terms of molecule equivalent. The number of ATP that you can create from one molecule of glucose. And then the more you create, the better it is. And with that argument, actually, fermentation is less efficient. But if you actually look at the thermodynamic efficiency, it's a different metric that has nothing to do with this equivalent notion. Here you find that fermentation in the physiological regime is actually thermodynamically more favorable. So that's also interesting. It's a different way of thinking. This equivalent way of thinking is not a thermodynamic way of thinking. It's a very different metric. So that's also an important message here. Yeah, so this you can do the same analysis for fermentation and respiration. Okay, I conclude. Yes, I think I went through all the key steps. I think what is interesting is with only topology and chemical potential of the terminal species, this is as far as you can go. I think now the next step is to include information about kinetics to try to rule out some gears. And I think these concepts are very general because I mostly focused on metabolic networks, but you could take any chemical reaction network and try to apply those networks. So I'm also very interested in starting to think about metabolic networks because they obviously have an important ecological role and what regulates those networks. These are key modern questions. How are we perturbing